Hello, good afternoon. We'll continue today our lecture. We will introduce the gravitational potential energy for objects. So what does gravitational potential energy mean? Any object, as we have seen earlier, has its own kinetic energy if it's moving from one position to another. There is another energy that is related to that object, that is related to the position of this object with respect to the ground, which means if I have an object going from point A to point B, I have the total energy being unchanged. However, it will be transformed from one kind to another. The expression that defines the gravitational potential energy is EP equals to mgy. So it is proportional to the mass, to the gravity, and to the location from the ground. The unit for the gravitational potential energy is joules as well, and that's also a scalar. So it is potential because if that object was released, this energy that's called potential energy will be transformed into kinetic energy in this case. So this potential energy is stored inside this object, and it is proportional to the location of this object from the ground. So EP equals to mgy. We'll see this example. In this example, we have an apple that has a mass of 200 grams, and it has a gravitational potential energy of 4 joules while it's on the tree due to its height, again, because we said it is proportional to the height. How high above the ground is the apple? Assume the G is 10 meter per second square for simplicity. So let's do the calculation. So if we have an apple that has a mass of 0.2 kilograms, right? And it is sitting on the tree. Has a gravitational potential energy of 4 joules. We need to calculate the height of this apple. So the height is unknown. G is 10 meter per second squared. Now, when this apple is sitting on the tree, this means its velocity is 0, right? So we know that the velocity here is 0. Let's call it V1. So in this case, I can calculate EP1 as mgy, that is unknown. Y here is unknown. And we know that the gravitational potential energy is 4 joules. We know that EP is 4 joules. So in this case, I have 4 equals 2. We will see how this is going to contribute later on when we do the conservation of energy. But right now, I have the gravitational potential energy as 4 joules. I have the mass as 0.2. I have the acceleration here as 10, I need to calculate y. So in this case, y is 4 divided by 0.2 times 10, and y equals 2 meters. So back to the question. The answer is B, 2 meters. So this is how we calculate the gravitational potential energy, or we calculate the height of any object that has a specific mass, if I know its gravitational potential energy. Now this takes me now to the conservation of energy concept that I have mentioned earlier. So let's look at this example. So if we have a free fall, for example, a ball that you are throwing all the way up with an initial speed of 2 meters per second, what's going to happen to this ball? This ball is going to go up. You give it initial velocity up. It's going to go up all the way till, so it has an initial speed here till it reaches a point where this speed becomes 0. So when you give it an initial speed here, basically you give it left that point with a specific kinetic energy, and also it has, let's assume that this is the ground. It has a gravitational potential energy with respect to the ground. So what's going to happen is the total energy right at this point here will be the same as the total energy right at that point. However, at this point, the kinetic energy will be different than this point. At this point, because it reaches a velocity of 0, the kinetic energy is going to be 0, and all the energy here will be potential energy. However, right at this point, it will be a mix of kinetic energy and potential energy. So it is very important to understand that the energy, the conservation of energy, means that the energy is not going to be destroyed or will not be created. The energy is going to be transformed from one form to another. For example, here it has a kinetic energy, EK, we call it 1, and also has a potential energy. Let me call this one EP1, the gravitational potential energy. Here at this position, the EK2, because the speed is 0, this will be 0, plus EP2. Right at this point, the potential energy will be maximum. So when the ball leaves this position and goes up, the kinetic energy will start to decrease. The potential energy will start to increase till it reaches to this point where the kinetic energy becomes 0 and the potential energy becomes maximum. Okay? So at the end, EK2 plus EP2 equals to EK1 plus EP1. Then once it reaches the highest point where the kinetic energy becomes 0 and the potential energy becomes maximum, then will start to fall back again. Then the kinetic energy will start to increase and the potential energy will start to decrease till it reaches this point. Now let's look at this example. In this example, we have a ball that has a mass of 2 kilograms directly upwards with an initial speed of 2 meters per second. The ball rises to a maximum height of 0.204 meter before falling back down again. Observe this. Set the lowest point, which is your hand, the location where you threw the ball, as y equals to 0. Now, what we need to do is we need to do the conservation of energy balance and see how the energy is being transformed, as we said. So let's go back to the example that we started here. Here in this example, where I throw the ball, I will be assuming that this is my y equals to 0. So let me erase this and we'll start. So here, this is y equals to 0. This is my reference point. I have the mass as 2 kilograms. I have the height the speed as 2 meters per second, and the maximum height is 0.204. So the speed here is 2 meters per second, and I have the height as 0.204 meter. Let me now look at the total energy at those two locations and compare them. So for this position here, the initial, so this is initial, this is final. I have the kinetic energy, so let me call this one initial position. I have V as 2 meters per second, right? So I can calculate EK1 to have M V1 squared, and in this case EK1 will be half times 2 times also 2 squared. EK1 equals to 4 joules. Let's evaluate the potential energy, the gravitational potential energy, EP1, at y equals to 0, mgy, this is 0. So it is very important to notice that the total energy right at this location, which is EK1 plus EP1, is 4 joules. And it is also important to know that right at this point, the total energy will also be 4 joules. But let's evaluate what is EK2 and EP2 would be. So EK2 half mv squared, because the speed is 0, then EK2 is 0. What about EP2? EP2 is mgy, and in this case EP2 is M is 2 kilogram times 9.8. The question did not say 2 times 0.204. EP2 equals to almost 4. 2 times 9.8 times 0.204 is 3.9984, which means EP2 is 4. So notice now, with the conservation of energy, I have EK1 plus EP1 equals to EK2 plus EP2, right? So, and here both are 4 joules. So to understand this, let me look at the ball. This is the ball at the final destination, which is at 0.204, and this is the ball at 0. So this is y equals 0, my reference. And here is 0.204 meter. So the energy is, total energy is 4. But what's happening here, if I am to look at EP1, let me put them here. If I'm looking at EP and EK. So here, EP was 0. EK was 4 joules, right? Here, at this position, EK was 0 and EP was 4 joules. Now, if I am to look, for example, let's assume in between. So if I am to move in this direction, then the potential energy will start to increase. Let's assume that it became 1. Assume that it became 1. Then definitely the kinetic energy will decrease to 3. Let's assume that this one went higher, became 2. This one becomes 2. And then went further higher. Then this one becomes 1. And then this one becomes a 3. And then reached the maximum height. At that maximum height, the EK, the kinetic energy becomes 0, and the gravitational potential energy becomes 4. So always EK plus EP for initial equals to EK plus EP for final. Even for the intermediate stages, so here also EK plus EP equals to the EK plus EP here equals to the EK plus EP here. So the energy, the total energy is the same for all of them.